Good morning and welcome to AFD'S Academy. I am Arthur Francis Debam. Today, we're going to go through revision on redox TITRIMETRIC reactions, which means that we have normal volumetric reactions where we carry out our reactions during our titration and all of that. But in this case, instead of the normal volumetric reaction, we're going to be dealing with TITRIMETRIC reactions. So that is what we're going to be dealing with right now. But before we go in fully into all of these, trust me, I have to take you a little back on how to carry out the normal reactions of volumetric and how to calculate certain other volumetric reactions too, so that we can correlate all of these together. So let's see what we do. When I give us a question, all right, I'll also go in addition to that with the formulas alongside, because I've given us all the formulas which we're going to be dealing with. But I only hope that this time around, I can start giving us the formulas, but whatever the question is, I bring the formula elucidated, then we proceed with it. So let's start with a common one. Okay, our usual. So I am going to read the question, after which I'll state the given. Then we solve together. So it says that A is a solution containing 6.3 GDMQ of impure ethane dioxide acid, while B is a 0.10 mole per GMQ of sodium hydroxide solution. Then it says 25 cm cube of B gives 20.57 cm cube of A during a reaction. If the equation of reaction is given as, which I'm going to state, we should calculate the concentration of A in mole per dm cube, concentration of B in GDM cube, and the percentage purity. So let's see. I will state the given, then we start the solving. So we have our A, which is the acid. Is a solution containing ethane dioxide acid. And B contains sodium hydroxide. Now, in A, let's say 6.3 GDM cube of impure ethane dioxide acid. So this is the mass concentration, GDMQ. Mass con of impure is 6.3. B contains CB, concentration of the base, is 0.10. Now, if 25 of B, volume of the base is 25 cm cubed, give us the volume of the acid is 20.57. And the equation of reaction has been given. So from there, we're going to get our Na, Nb. So I'll write it out, but I'll take it out later. So from the equation of reaction, we know that the number of moles of the acid is 1, and the number of moles of the base is 2. So from here, we're going to see what they're asking us to calculate. The first thing is concentration of solution A in mole per dm cube. Con of A in mole per dm cube. Now, how do we calculate the concentration of A in mole per GNQ? Remember, we have two ways, or even three formulas which you can use to calculate the molar concentration. We say that molar concentration equals to amount over volume, and the same molar concentration is mass con over relative molecular mass, and the same molar concentration can be gotten by using CAVA formula. So there are three formulas which you can use to that end. Now, our job is to calculate our CA. Let me put it here, CA, which we don't know now. So I want to do that, but I can only start by bringing out the formulas. So let me use that formula for us to get the concentration of phase. I'm going to take, okay, it doesn't mean I can continue. So 1 in mole per dm³, which is the molar concentration. We can achieve that by using the formula CAVA, CBVB is equals to NA over NB. Now, if I make my CA the subject, CA would be CBVBNA over, remember I'm calculating the concentration of the acid. So CBVBNA over VANB, and this is equals to, the concentration of the base is given to be 0.10 mole per dm³ times the volume of the base is 25 times the number of moles of acid is 1 all over volume of the acid is 20.57 cm³ times number of moles of the base is 2, and this all is equals to what? So we are going to do the calculations here. 0.1 times 25 divided by 20.57 and also divided by 2. We have 0.0608. 0.0608 mole per dm³. 0.0608 mole per dm³. So first thing first, we've gotten our molar concentration of the acid. Now let's listen to the next question so that we can see what to do. Concentration of solution A in GDM³. So we have to calculate the mass concentration. Remember, this is the GDM³ of impure. It therefore means that there is a mass concentration of what? Pure. So for us to get that mass concentration, the formula, we have a lot of them too, I think a couple of them. We have them in mass over volume in GMQ, which of course is not it. And we also have another one, which is molar con times relative molecular mass. So we are going to calculate our molar concentration, which we've gotten here already to be this, times the relative molecular mass, which means you have to determine the relative molecular mass of it, the ethane diop acid. When we do that, we now have the mass concentration of the pure ethane diop acid. So permit me, I have to take this out. Okay, let me take this out. Now, 2 mass con of pure A, that's sample A, is equals to molar con of A times relative molecular mass of A. Now, let us determine the relative molecular mass first. H2C2O4. Now, hydrogen mass number is 1, so 1 times 2 plus carbon is 12, 12 times 2 plus oxygen is 16, 16 times 4. So if you go through all of these, we have 2 here, we have 24 here, and we have 64 here. Now if I add 60 plus 2 is 88, 90. So I have 90 gmol. So this is just by the side. So I can come back here, I have my molar concentration of the acid. Molar count of the acid Ca is 0.0608 mole per dm3 times the relative molecular mass of A, which I've gotten there, is 90 gmol. And this is equals to, I have this times 90, 5.46 or 5.47. I have 5.47 GDNQ of pure E. Now it's time for me to take out the equation of reaction so that I can add more to what is required. GDNQ of pure A is equals to 5.47 GDNQ. All right. Now something is very important here. Why are we looking for the mass concentration of pure, the mass concentration of impure, and all of that? It's because there is a question that says the percentage purity. And if you remember, percentage purity is equal to the mass count of pure over the mass count of impure times 100. That is it. So we have to determine this by virtue of the fact that there is a question that talks about purity or impurity. Our mind should go back to calculating this and this, even if we weren't told. Sometimes they can just give us the whole question, and the only question you see is calculate the percentage impurity of A. Now, from the formula of percentage impurity, you will know that you have to determine the mass count of pure, the mass count of impure, and all of that. Otherwise, you're going to be lost alongside. Our job today, we're going to focus more on purity and impurity, and in both sides, redox and the other one. So I need to introduce this to us so that we can, when we move into redox, you're not going to be confused, especially with the formulas of the CAV. You now get accustomed to that reality before I switch over. So now that is it. The next question says, hence the percentage purity. Now, let me take this out now so I can deal with percentage purity. So C, or 3, percentage purity equals to mass count of pure over mass count of impure times 100. Now the mass count of pure is 5.47. 5.47. That of impure is 6.3. 6.3 times 100. And this all is equals to, now 5.47 divided by 6.3 times 100. It is 6.8. So we have 86.8%. So the ethane acid is 86.8% pure. That's relatively pure. Let's put it that way. All right. Now, another thing, I want you to understand, why is the purity, mass count of purity, lower than that of impurity? Okay. If this is a sample A, it is having some impurity, let's say 20 GDNQ. The mass count here is 20 with impurity. Then this is a sample P gotten from here. We have removed all the impurities. and what is left naturally should be less than what is here. If this is a sample 20 grams per DMQ contains impurity and you are instructed to remove the impurities, then take note of the mass. The mass is meant to be reduced. Okay, another practical example. If I give you a cup of rice to cook, and I say just rice, I don't want nothing else in it other than rice. And in that cup of rice, you decide to spot it, you thereby saw a lot of bean seed in it, a lot of them. Now, you understood the principle or the law, which I told you, I need just rice. Now, the beans therein are acting or serving as what the impurities, which means you must remove them. Remember, it was 1 full cup. And now, 1 full cup of rice, you haven't taken like 100 seeds of bean seeds, you realize that the quantity will reduce. It will no longer be full cup. So the grammage is meant to reduce. So that is the reason why the percentage, the mass count of pure is meant and always meant to be lower than that of what? Impure. So in your calculations, whenever probably you're carrying out your calculations, you can make mistakes. We make mistakes. Everybody makes mistakes. In the course of doing that, you decide, you now saw that the mass concentration of pure is higher than that of impure. Then something is wrong. You have to trace it up. So this is it. We're done with this question. We're going to take another question. Okay. All right. A is a solution of hydrochloric acid containing 5.00 GDMQ. B is a solution of impure potassium hydroxide containing 6.50 GDMQ. Now, 25 of we are to put A into the burette and titrate it against 25 cm cube of B using methyl orange. And after that, the endpoint is 19.10. Using the equation of reaction given here below, we should calculate the concentration of A in mole per dm cube, concentration of B in mole per dm cube, percentage purity of potassium hydroxide. So this is almost similar to what we've done. Remember, percentage purity, what's the formula? Is mass count of pure over mass count of impure times 100. No, all time. You should take note of that. So let me take care of this again. The given here, we have our A and our B. A is HCl, and B is potassium hydroxide. Volume of the base is 25 cm cube. Volume of the acid is 19.10. Okay. A is a solution containing this, GDNQ. So the GDNQ mass concentration of A, GDNQ of A is 5.00 GDNQ. Now this GDNQ, what does it mean? It means mass concentration. So the unit is GDNQ. I do not want to take the pain of writing mass concentration. Just know the unit GDNQ is standing for what? Mass concentration. If I say mole per DNQ, I'm referring to molar concentration. If I say mole, I'm referring to amount, and so on. Now, it says that that of impure B is 6.5. Impure GDMQ of B is 6.50 GDM. With the equation of reaction, which is HCl plus potassium hydroxide, which gives us potassium chloride plus water. 1, 2, 2 hydrogen, oxygen is 1, chlorine is 1, potassium is 1. So from here, our number of moles of acid is 1, and our number of moles of base is 1. All right, I'm taking this out. Take note. What again? That's all that was given. So the next question says we should, from the result, obtain all of that. We should calculate concentration of A in mole per dm³. Question number 1. Con of A in mole per dm³. Now we have to look at the formula, or the best formula to be used. We are asked to calculate the molar concentration of the acid. And we have various formulas for that. We have the CAVA. Let's see, can we use that? Now, the concentration of the base is not given. The concentration, that of the base is not given, so it means the CAVA formula cannot be used because the two variables, CA and CB, are not given. So that formula is out. The second formula is amount over volume of the acids. There is no amount given, although we have a volume here, but there's no amount. So that formula is also out. The third formula, molar con, is equal to mass concentration over relative molecular mass. Yes, we can use that. The mass concentration is given here to be 5. The relative molecular mass, we can determine it from here. So it is expedient. It is not just by you knowing how to solve all of this. You must have the formulas too in your head. If you do not have a fervent grasp of the formulas, then you cannot go through this at all. You're going to be found wanting in one way or the other in the course of dealing with the calculations that have to do with this. So we are going to use that formula, which is mass concentration, mass con of A over relative molecular mass of A. Now, the mass con of A is given to be 5.00 GDM³ over the relative molecular mass of HCl is 36.5 G-mole. Now, how do we get that? This is HCl. Hydrogen has a mass number of 1, plus chlorine has a mass number of 35.5. If you add this, you have 36.5. So that's how we got 36.5. And this all is equals to, so I have 5 all right, 5 divided by 36.5 is 0.137 mole per dm³. Now, CA is 0.137 mole per dm³. Now, let's see. All right, we're good. So we've gotten this. Now, what's the next question? Having gotten that, this is concentration of B in mole per dm³. Remember, we've gotten the concentration of A in mole per dm³, which is this. Now, they are asking us to calculate the concentration of B in mole per dm³. Remember, before now, we never had Ca, so we said we cannot use the formula CAVA. But now we've gotten our Ca. Therefore, the formula that we can easily use now becomes the CAVA because we have one of them, two variables known. The other one, which is unknown, is what will make the subject. So by virtue of that, we can proceed with this. Now, let me take this out. Concentration of B. Con of B in mole per dm³. which is, we use the formula CAVA over CBVB is equals to NA over NB. Now I'm looking for CB now. CB is equals to CAVA NB over VB NA. And this is equals to my CA, okay, let me put in the variables. I've not included them yet. Now my CA here is 0.137 mole per dm³ times volume of the acids is 19.10 cm³ times 1 all over the volume of the base is 25 cm³ times number of moles of the acid is 1, and this is equals to 0.137 times 19.10 divided by 25, 0.105. This is 0.105 mole per dm³. So I come back here, I have my CB is equals to 0.105 mole per dm³. So I've gotten the concentration of the base in mole per dm³. Remember, they give us the mass ton of the impure to be this. Now, let me see the next question. Percentage purity of KOH. So they are moving straight up to tell us to calculate the percentage purity. But remember, before you get your percentage purity, let me write the formula out so that we'll see. Thirdly, percentage purity, which is mass ton of pure B over mass ton of impure B times 100. Now, they give us the mass ton of impure B, which is here. The mass ton of pure B, we don't know. So they will not tell you to calculate. Some questions will say, calculate the mass concentration of the base. That calculation which you're going to do becomes the mass ton of what? Pure. But now they did not tell us. They need us to understand, by virtue of this formula, if we know this formula and we have imputed the variable, we should know that something is missing. That thing that is missing, we have to thereby look for it. So we can now proceed. How then, before I begin to make use of this, I should be able to get my mass concentration of what? Of pure B. So I'm going to do that down here. So then take it out and replace them back. Therefore, mass con of pure. Mass concentration is what? Molar con times relative molecular mass. So I will multiply that. The molar con is 0.105 mole per dm³ times the relative molecular mass of KOH, 39 plus 1 is 40 plus 16. That's 56. 56 G mole. Okay. If we do this, then we're going to multiply. Let's have it 0.105 times 56 is equal to 5.88. So this is 5.88 GDM³. So if this is true, remember I told us earlier on that the mass concentration of pure must be less than that of impure. Look at that, this is that of impure, and this is pure. Whenever this is higher than that, something is wrong, maybe in our calculation or in the question. So let me put it down here. GDNQ of pure is equals to 5.88 GDNQ. All right, now I can take this out, substitute the variables here, and I get my percentage purity. So this is done. Let me take it out. I just want us to see from the formula that we'll be able to know that it is not in all cases they give us complete questions. We determine the leftovers by our own self, by our understanding of the context, of the topic, of the calculations, the ring, and importantly, of the formulas. So let me take this out now. Therefore, if that is true, mass count of pure is 5.88 over that of impure is 6.5 times 100, and this is equals to what? 5.88 divided by 6.5 times 100. We have 90.5. So this is 90.5% pure. That is very high. So we're going to take more questions so that we'll be able to move on. Now, these which we've done are just focused on purity. I will take some on water of crystallization, maybe the ones that are probably you are acquainted with, you know already, before we drift or we're going to move a little bit away from that. So this is on purity. Don't forget, what is the formulas? Percentage purity is equal to mass count of pure by mass count of impure times 100. Percentage impurity is equal to mass count of impure minus that of pure over impure times 100. That is important. You have this in your materials in your notes. You go through them and get yourself acquainted with it. And it is important that when you're solving all of this, your answers, the units are very important. I've seen in scenarios in your practical work where you have your answers, the unit is not correct. That is wrong. It is obviously wrong. So you must have a correct word unit so that we know that this is what you meant. If I'm talking about mole per GN cube and I have mole, it is not the same thing. Mole means amount, as the unit says. And I am referring to molar concentration, so they are not the same. So work on your unit and ensure that you have the right thing done. Now, let's take some question on the percentage of water of crystallization. Okay, first of all, percentage of water of crystallization. We know that the formula basically is, we can just directly say the relative molecular mass of that of water over the total compound times 100. That we know is simple, is straightforward. But before we get to that particular part, we always get accustomed to the question that comes before it, the number of moles of water of crystallization, X. Then, instead, when we get that, it speeds up our rate of reaction in terms of our understanding of the rest, because without that X, we cannot name the compound therein. So, and that formula seems a little complicated, and it is the most difficult of the whole formulas when it comes to water of crystallization. But we have to understand it first. If we understand that and how to go about it, then every other thing is sorted out. So I'm going to state that formula. That formula should give us almost an overview of everything which we need, so that then we can continue. So I'm going to use that formula to explain everything about water of crystallization before I move forward. So now, X is what we are, number of moles of water of crystallization. How do we get that? We say that mass count of hydrated over relative molecular mass of hydrated is equals to mass ton of anhydrous over relative molecular mass of anhydrous. Now, if this is it, all right? Now, let us look at the formula itself. It means that for us to be able to do anything that has to or pertains to this reaction, we must understand what is hydrated substance, what are anhydrous substances, how do they come about? You see how significant that is. So when we talk about water of crystallization, we are technically referring to that salt that contains water in it. There are certain salt samples, when you expose them to the atmosphere, they absorb so much water that they could become solutions. Those are deliquescent substances. Then there are some that when you expose them, they absorb a little water to become moist. Those are hygroscopic substances. And there are substances when you expose them to the atmosphere, they lost almost all of their water. Those are efflorescent substances. If you check sodium hydroxide, for example, open it and keep, before you come back the next day, you see water. Okay, they are deliquescent. Even your normal table salt, sodium chloride, the one used in cooking, expose it and leave it for a couple of days or thereabout. You come back and see water in it because it has absorbed moisture. So when we do that, we're going to calculate in a particular salt that contains water in it. It could be 7 moles of water, which is heptahydrate, decahydrate, dihydrate, tetrahydrate, whatever it is. We will always and all the time have to calculate the mass concentration of that and that of anhydrous. So let me give us an example. If we have Na2CO3, the 7 moles of water, this is a sample, a clear sample of salt that contains water in it. So this salt, sodium carbonate 4, contains 7 moles of water, okay, of crystallization. It contains 7. Now, if I take this out, only this, if I have this is sodium carbonate 4 anhydrous. It means it does not contain water of crystallization because there is no water attached to it, all right? But if I hold it together with this, it is hydrated because it contains water. So from the formula, if you say mass ton of hydrated, means we are looking for the molar concentration of the whole of this compound. If we say mass ton of anhydrous, we're looking for the mass ton of only this. The relative molecular mass of hydrated means we're going to look for all of this. And that of anhydrous, just this. Take note, it is significant. If you understand this, then you can deal with it. If you don't understand this thing, you don't know which one is which. So that is why I have to explain it a little bit before we get into it. So let's take a question first. When we solve it together, we'll see how things are going to be or turn out to be. I'll read the question, state the given, then proceed on later on. Okay. Solution A contains 20 grams of ethane acid crystals in 1 dm cube of the solution. Solution B is a solution of sodium hydroxide containing 0.5 mol per dm cube. Now, if 25 cm cube of B gives 41.63 cm cube of A, in the given reaction, from the equation of reaction given, they've given us the equation of reaction, we should calculate concentration of A in mole per dm cube, number of water molecules in 1 mole of ethane acid crystals are the number of moles of water of crystallization, and percentage by mass of water molecule, which is the percentage of water of crystallization. All right. So let me state out the given, then from there we proceed forward. So I have A is ethane acid crystals. This is A, which is H2C2O4. Okay. That contains, I need to check that out. It contains X water. So this is X water. or let me write it this way. So it means it contains water in it. Then B, so B is what? What DNQ? B is a solution of sodium hydroxide. So this is NaOH. Now, A contains 20 grams of the crystal. So the water, the GDNQ of the hydrated substance is given. So GDNQ or hydrated or hydrate is given to be 20 GDNQ. Okay, we'll continue. And CB is, let me check, it is given here also. 0.5, you see solution B is a solution of sodium hydroxide contains 0.5 mole per GNQ. So here I have 0.5 mole per GNQ. That's the molar count. Let's see, that is all. They didn't give us that of A. Now, we've gotten this. So we can actually come back. The volume of the base is 25 cm cube. Volume of the acid is given to be 41.63 cm cube. And the equation of reaction, we are going to be able to get our number of moles of acid and our number of moles of base. Is given to be, that of base is 2 and that of acid is 1. Let me give us the equation so that you see if I take it out. We have 2 moles of sodium hydroxide plus H2C2O4 X water, which gives us Na2C2O4 plus X water plus 2 moles of water. So this is it. Now from here, number of moles of the base is given to be 2, number of moles of the acid is 1. And the equation is balanced. But this is for the hydrated, which means from the formula, we are going to calculate for anhydrous, which means the anhydrous must not contain the X water. We're going to take out the X water from the anhydrous. Then we deal with only this when it comes to that. But from the questions given here, we've gotten the concentration of the base. The count of the acid is not given. Ca, it seems we're going to calculate it. So let's see what I say. First question on that. Concentration, calculate the concentration of A in mole per DNQ. So we are going to calculate the concentration of the acid, Ca, first. So, question number 1. Count of A. We use the formula CAVA over CBVB is equals to NA over ND. And this is CA, which we are looking for, is equals to CBVB NA over VA ND. And this is equals to, the concentration of the base is given to be 0.5, so I have 0.5 mole per DNQ. Volume of the base is given to be 25, so I have 25 cm3. Number of moles of the acid, Na is 1, all over. Volume of the acid is 41.63 cm3 times 2. Number of moles of the base, Nd, is 2. So, in that case, let's see what we're going to get through our calculator. So I have 0.5 times 25 divided by 41.63 divided by 2. 0.150. So we say the concentration of the acid is 0.150 mole per dm cube. So that is it. Gotten that. So if that is true, let's take our next question. Question number 2. Number of moles of water of crystallization. Now we're going to calculate the number of moles of water of crystallization. For us to be able to calculate the number of moles of water of crystallization, don't forget that we have to know the mass concentration of the hydrated, which is given, and the mass concentration of the anhydrous. Anhydrous of what? A. So I'm going to take this out so that I can calculate the mass count of the anhydrous. Now, GDM cube of anhydrous is what? We don't know. So, by calculating the mass count of anhydrous, the formula mass count is what? Molar count times relative molecular mass. So, the molar count of sample A times the relative molecular mass of anhydrous A. So the molar count, so here we go, GDM cube of that A is equal to the molar count of A, which we just got here to be 0.150 mole per dm cube, times anhydrous A. Anhydrous means from year to year is anhydrous. If I add this, it is hydrated. So anhydrous A means I'm taking year out. So I have to calculate the relative molecular mass of this only, and that is 90. So this is 90 g mole. Now, if you are, or if you may ask, how do you get 90? I'll bring it down here again. H2C2O4. Hydrogen is 1. 1 times 2 plus carbon is 12 times 2 plus oxygen is 16 times 4. So when you do all of this plus this, you get 90. So this is equal to, I multiply 0.150 times 90, it's 13.5. So it's 13.5 GDN cube. So here is 13.5 GDN cube. And don't forget that the mass concentration of the anhydrous must be lower than that of hydrated. I have a cup of salt and there is water in it. If you weigh it, it's meant to be, let me say it's 200. If I decide to take that salt, put it on the fire and heat it for the water to go, what will be left must be lower than what it was. So that is the reason why the mass count of hydrated should be higher than that of anhydrous, because it does not contain water again. And this is the hydrated, which is 20, and this is anhydrous, there's no water, is 13.5. So if the reverse becomes the case, you should know that you are doing something wrong. It is important in the case, or in the course of you practicing, you will see a whole lot of those kind of errors. And when you do, take note of that. So here we are, let's take this out and move on. So we calculated this. The next question says, number of moles of water of crystallization, which is X. For us to get that, remember I told us we must get this, which we have. So the number of moles, the formula is X is equals to the mass count of hydrated. Let's take it like that. I don't want to be writing the formulas again. The mass count of hydrated, which is 20, over the relative molecular mass of hydrated, which is 90 plus X 18. Hydrogen is 1. 1 times 2 is 2. 2 plus 16 is 18. So this is the X 18. Because hydrated contains 90 plus X 18. This is it. This is equals to the mass count of anhydrous is 13.5 over the relative molecular mass of anhydrous without water, which is 90. So we are meant to make X, which is here. Remember, let me call it number of moles. Number of moles of water of crystallization. So write all of it. Just take note that this is number of moles of water of crystallization. So we'll be able to get our X. And when we get our X, then we can calculate the percentage. All right? So from here, if I want to make what I'm looking for, should always be by my left-hand side when I'm making what change of subject or formula. So this becomes first. So I have 13.5 open bracket 90 plus x18 is equals to 20 times 90. This is equals to, let's come here, 13.5 times 90. 13.5 times 90 is 1215. 1215. Now 13.5 times 18, x. 13.5 times 18 is 243 plus 243x. This is equals to 20 times 90. 20 times 90, 1800. So I have my 1800. Now, if I want to make x the subject, I will take this across the quality sign. So I have 243x is equals to 1800 minus 1215, and 243x is equals to 1800 minus 1215, 585. 85. Therefore, if I divide both sides by 243, 243, 243, my x is equals to what? 585 divided by 243, that is 2.4. So 2.4. So the number of moles of water is 2.4. So that is that about that. So we've gotten our x. Now, if that is true, the next thing is to calculate the percentage of water. I want to know the percentage of water that was in the source sample. So I'm going to take this out so that we can do that. So let's take it out. Lastly, percentage of water of crystallization is equals to X water over the whole compound, H2C2O4X water times 100. And this is 2.418 over 90 plus 2.418 times 100. This is what? 2.4 times 18. X, remember, we just finished calculating it. X is 2.4. So the number of moles of water is 2.4. So we put our 2.4 here. 2.4 times 18. What do we have? So I'll do that. 2.4 times 18 is 43.2. Take note. 43.2. Okay, divide by, okay, 43.2 plus 90 first. 133.2. 133.2 times 100. Now, if we come back here, we have this times this give us 43.2. Divide by 90 plus 43.2 give us 133.2 times 100. And that is equals to what? Now, 43.2 divided by 133.2 times 100 is equals to 32.4. So we have 32.4%. So the number of moles of water was not very much. Is 32.4% of water that was in the sample. All right. So there will be some samples that will contain almost 90-something percent or 80-something percent. So that will also go with the number of moles of X, number of moles of water crystallization, which is 2.4. In those scenario, could be maybe 8, 9, or 10. Okay, let's take another question. Straight up. Okay, here we are. Let me take this out. Okay. We say A is a solution of KMnO4. Now, this question is a redox question. It's straight up on redox now. Let us take a careful observation of that. The formula first on redox, before I continue with the question, let us understand how that is being applied. We have our CAVA over CBVB equals to NA over NB, when we are dealing with normal volumetric analysis. But in case of redox, we have concentration of oxidizing agent times volume of oxidizing agent over concentration of reducing agent times volume of reducing agent. This is equal to the number of moles of oxidizing agent over number of moles of reducing agent. So where we're calling concentration of the acid, here we're saying concentration of oxidizing agent. So the two reactants will be the one oxidizing agent, one reducing agent. So we'll be able to identify that and also know. I've given us this kind of stuff before in the redox calculations, so I believe you will not be too far away from the reality. So in that scenario, whenever we come across a redox question, this is what we use. We don't use this. If you use this, you're still going to get the answer correctly. But the formula is not very 100% correct. It's wrong because you are not dealing with normal acids. You are dealing with oxidizing agent this time around. So we're going to take our first question here, then we apply this principle and see how that goes. And it is on this note that we have to also have carried out balancing of redox reactions. If you do not know how to balance the redox reactions and it is not given to you, then that question cannot be solved. So it is important that you have to first of all go learn how to balance redox equation or redox reactions, which we started from our understanding of oxidation numbers, how to calculate oxidation number of element or compounds, and thereby we move forward to balancing of redox using oxidation number method because it is easy and correlative, and thereby we can now proceed in advancement to applying that knowledge into this. But if you do not know how to balance the whole equation of reaction, the question will be given to you sometimes without the equation of reaction. At least for those in the university, in the secondary school level, the West African Examination Council can always give you the balanced reaction. But this is, if it is in the university setting, it is expedient that the students should know how to do that. So you're not going to hold the lecturer responsible for not giving the equation of reaction because the lecturer must have taught you on how to balance that. So go and sort it out again and go through it. I can't start doing that right now because of the complexity of the balancing of redox. It's going to take us a long time. So let's move forward. Just go back and check one of our videos which we've done earlier on balancing of redox. You're going to see them all and study them carefully. If you do not understand anything, you can reach out to me through questions or through the comment section. You can reach out to me. And once more, if you have not subscribed to the channel, you are doing yourself a disservice because most of the important variables which we're going to be dealing with right now, which are meant to pop up in your phone through notification, and you do not have, you're not a member, you've not subscribed, then you can't get that information. All of that is going to be passing you by. So it is important you do the needful by subscribing and on your notification bell. I will always reach out to you when you need me the most. Trust me. Let's take a question now. I'll read, like I said, and put the other variables down, okay? Let's take them out. We say A is a solution of KMnO4. B is 0.02 mole per GN cube of ethane dioic acid. And solution C is 1.0 mole per GN cube of concentrated tetraoxosulfate 6 acid. You know, in redox reactions, many a time we do not use an indicator. We only acidify the system when, especially we are making use of KMnO4. We acidify it by using H2SO4. So that is exactly what is playing out here. Now we say titrate solution A against 25 of solution B, which has been acidified with 5 cm cube of solution C. Average volume of 16.5 of A was required for complete oxidation of solution B. From the result obtained, we should calculate the concentration of solution A in mole per dn cube. Okay. Concentration of solution A in GDN cube. Equation of reaction is given. So I'm going to give you the equation of reaction. But before I do that, let us take out the A and the B in the given. This is A, and this is B. Okay. A is a solution of KMnO4, KMnO4. B is 0.02 mole per dn cube of ethane dioic acid. So here is H2C2O4, ethane dioic acid. Now, they've given us the concentration of the reducing agent. This is the oxidizing agent, the COA, and this is the reducing agent, the CRA. So I have concentration of reducing agent is given to the, let me go through it again, 0.02. So I have 0.02 mole per dn cube. All right. Acidified by that. Now 25 titrate solution A against 25 cm of solution B. This is B. So volume of reducing agent is 25 cm cube. And we're told that 16.5 cm cube, you say 16.5 cm cube of A was required. So the volume of the oxidizing agent is 16. So 16, what is it? 16.5. 16.5 cm cube. Okay. With the equation of reaction, I think that is all. So we are going to take the equation of reaction. I'll give you the equation of reaction, then I'll take it out. The equation of reaction, which is 2MnO4 minus plus 5 C2O4 2 minus plus 16H plus gives us 2Mn2 plus 10 CO2 plus 8 moles of water. This is it. So by that, number of moles of oxidizing agent is 2. Number of moles of reducing agent is 5. So this is it. We are on redox. The advantage we are having right now is that the equation of reaction has been given to us. Had it been they never gave us this equation of reaction, we will be bound to balance it ourselves. And in the course of balancing, if we miss anything, we likely miss this number of moles of the oxidizing agent and reducing agent. And these things are cardinal. Well, once you miss these two variables, they are not correct. There is no way on this planet that you're going to get that answer correct. You're going to be lost completely. So it is essential Because when things like this comes out in the exam, which they must, compulsory, they must come out. And when they come out in your exams, you're obviously going to balance the equation of reaction yourself. So the simplest question that you would have been able to try without stress becomes the most difficult because you never practiced one of the sections which you should have done before now, which is balancing of the redox. It is that important. So in case you are not acquainted with the balancing, you have to go check it out. And anywhere you do not understand, you can always reach out so that we'll be able to sort it out together. So that is it. Go through all of these and let's see what plays out. Now, I want to take this out. Okay, I mean, not necessarily have to. Let's go straight to the question. Concentration of solution A in mole per dm. We are asked to calculate the concentration of the oxidizing agent. Remember, they've given us the concentration of the reducing agent here to be this, and that of the oxidizing agent, we don't know. That is what we want to calculate right now. So we're going to use our formula, which is concentration of oxidizing agent times volume of oxidizing agent over concentration of reducing agent times volume of reducing agent equals to number of moles of oxidizing agent over number of moles of reducing agent. And we're calculating the concentration of the oxidizing agent. So concentration of oxidizing agent is equals to the concentration of reducing agent times volume of reducing agent times number of moles of oxidizing agent all over volume of oxidizing agent times number of moles of reducing agent. And this is equals to, let's substitute the variables in it. Concentration of reducing agent is given to be 0.02. So I have 0.02 mole per dm times volume of reducing agent. The volume of reducing agent is 25 cm. Times number of moles of oxidizing agent. Oxidizing agent is 2. All over volume of oxidizing agent. The volume of oxidizing agent is 16.5. Times number of moles of reducing agent. Reducing agent is 5. So all of that will proceed. So I will come back here to have my 0.0 molecular mass of what? Of the A, which is KMnO4. So we're going to know the mass number of base, and base. That is how significant it is. So in your exams, it will be given, okay? But then you should also get yourself acquainted with them so that you will not be lost in case the lecturer tends to forget and it's not there in the exam board for you to ask. So that is it. So let's take this out and sort it out for ourselves. So we want to calculate the mass concentration of the oxidizing agent KMnO4. Okay. 2. Mass con of A, which is molar con of A times relative molecular mass, which is the molar con is given to be 0.0121 mole per dm cube times the relative molecular mass. I'll have to look at it directly so that I wouldn't stress much of myself. Is 55. But this guy is 55. So potassium is 39 plus manganese, which is 55, plus oxygen. Manganese, which is 55, plus oxygen is 16 times. All right, sorry about that. Let's continue. Okay, I have to find out what that is. 0.0121 times, where is it? Are we multiplying at all? We are adding, not times. Plus 39. First of all, let me calculate this. That chord tends to distract me a little bit. We are going to multiply this, but let's find out this first. All right? 16 times 4, 16 times 4 equals to 64, plus 55, plus 39, which is 158. So I have 0.0121 mole per dm cube times 158 GDM cube. So this is equals to 0.0121 times 158. This is 1.91. I have 1.91 GDM cube. So this is the mass concentration therein. If you check it out, we've been able to calculate our molar concentration of the oxidizing agent, and this is the mass concentration of what? The same oxidizing agent. But our knowledge of knowing the relative molecular mass of the whole compound is expedient. Like I said, many a time, they may not give you, not because they don't want to give you, but probably because the person who is setting the question tends to forget. So this is our 39, this is 65 plus 16 times 4. And all of that, we got 158. We multiply that by this, by the formula which says molar count times relative molecular mass for mass concentration. So by this, we're able to get that. So far, I've been trying to relate the calculations of the normal volumetric analysis with that of Redox, because I know too well that that of Redox comes most when it comes to exams. So we do not care that much when it comes to normal volumetric analysis calculation, which you should be acquainted to by now, because all the time we'll be dealing with them. So that is it. You should get yourself in tune with that. So give us more questions so that let's see, the more we see and how we can resolve them all together. Okay, let's take a question here. We say 0.019 kMnO4 solution. We should put it in the borate and prepare 25 of 6.0 grams per dm of impure ethane dioxide acid solution into the conical flask. Okay, 25 of that. And 15 cm cube of dilute H2SO4 into the flask. Heat the mixture and titrate kMnO4 solution against hot impure ethane dioxide acid until the endpoint is reached. Tabulate your borate readings and the average volume of acid of the kMnO4. So we are going to list out the two things which we are going to be dealing with. So we have our A, let's call that A, which is kMnO4. And let's call this B, which is ethane dioxide acid, H2C2O4. Okay, now let's go down. It's a 0.019 solution in the borate of the kMnO4. That is the concentration of the oxidizing agent. Count of oxidizing agent is 0.019 mole per dm cube. Okay, if that is it, and we should prepare 25 cm cube of the reducing agent. Volume of reducing agent the volume of reducing agent is 25 cm cube. Okay, now We come back here, we have volume of oxidizing agent at the end of the titration is 23.50, 23.5 cm3. Equation of reaction will be given so we'll be able to determine the rest. Now, we do not know the molar concentration of the ethane dioxide acid, so we're going to leave it there. We'll move straight up to check the equation of reaction. If the equation of reaction is given, so here I will have number of moles of oxidizing agent. Here is concentration of reducing agent, number of moles of reducing agent. Now, equation of reaction. This is the equation of reaction. We have 2MnO4 minus plus 5C2O4 2 minus plus 4H plus give us 2Mn2 minus 2 plus 10CO2 plus 8H2O. So from the equation of reaction, we'll be able to determine the number of moles of oxidizing agent and the number of moles of reducing agent. So number of moles of oxidizing agent here is 2. Number of moles of reducing agent here is 5. Now, listen to the question again before we go solving it. It says put 0.019 kmn solution in the burette, prepare 25 of the impure ethane dioxide acid. Prepare 25 cm3 of 6.0 gram dn3 of impure ethane dioxide acid. So GDN3 of ethane dioxide acid, impure, GDN3 of impure is 6.0 GDN3. So now we have the mass concentration of the impure ethane dioxide acid is given. We will need, or we will be needed to calculate the mass concentration of pure before we can do anything about purity or thereabout. The question, the end says, what is this? Measure and this titrate this solution against impure this solution until the endpoint is reached. Tabulate this and all of that. And questions. Tabulate the this and the average volume of A used. Indicator given. Are there no questions? There should be questions here. Patience a little bit. Okay. Mass count of this. Percentage impurity. Okay, good. After that, say we are asked to calculate the percentage impurity of this. Direct percentage impurity. So let's see how that goes first of all. Now, for us to get our percentage impurity, we remember that percentage impurity is mass count of impure minus mass count of pure over mass count of what? Impure. Now, for you to be able to get the mass count of any of these, mass count itself is what? Molar count times relative molecular mass of B. So the molar count is not given here. So we have to calculate the molar count first before we'll be able to get the mass count of what? Pure, because impure is already given. So by virtue of that, we know directly that the first thing to be done, although they went straight up to just tell you, calculate the percentage impurity. By virtue of our understanding of these things, we know that we cannot get mass count of anything without knowing the molar concentration. So we'll go straight up to check the molar concentration of this. If it is not given, we calculate it. So that's what we're doing right now. So first thing first, which is calculate the molar count of B. And we can do that easily by using, remember this is redox. So we are going to use the formula concentration of oxidizing agent times volume of oxidizing agent over concentration of reducing agent times volume of reducing agent is equals to number of moles of oxidizing agent over number of moles of reducing agent. Now, this is the reducing agent. We are calculating the molar concentration of the reducing agent. And that is CRA. Therefore, CRA is equals to COA, VOA, NRA over VRA, NOA. This is equals to concentration of oxidizing agent is 0.019, 0.019 mole per dm cube. Volume of oxidizing agent is 23.5. Number of moles of reducing agent, is 5. All over volume of reducing agent is 25 times number of moles of oxidizing agent, is 2. And that all is equal to what? So we're going to find out and check it out for ourselves. So I have 0.019 times 23.5 times 5 divided by 50. 50, that's 25 times 2 will give us 50. So we have 0.0447. This is 0.0447 mole per dm. So I come back here, I have 0.0447 mole per dm. So now I have the molar concentration of the reducing agent. So the next thing is for me to now calculate the mass concentration of pure ethane dioxide because I have that of impure. All right. So if I do that, then I can apply the formula to get my percentage impurity. So I want to take out the formula so that I can add what I'm looking for. The equation of the reaction or formula. So from here, the next thing is I want to get my GDM cube of pure. And the GDM cube of pure, if I come here, I have my GDM cube. That's the mass concentration of pure ethane dioxide is equals to molar com times relative molecular mass. And the molar com is gotten to be 0.0447, 0.0447 mole per dm cube. And the relative molecular mass of this ethane dioxide is 90. I told us before, 90 g mole. 90 in the sense hydrogen is 1 times 2 is 2, plus oxygen is 12 times 2, 24. Plus carbon is 12 times 2, 24. Oxygen is 16 times 4, which is 64. If you add all of these, you get your 90. So that's how we got this 90. So we move further, 90 times 0.0447 is equals to 4.023. So this is 4.023 GDMQ of pure. So this is 4.023 GDMQ. Remember, I've told us that the mass concentration of impure must be greater than that of pure. If you look here, you see that it's true. So anytime the pure becomes bigger than or greater or much more than that of impure, know that something is wrong. Probably in our calculations, there must be maybe an error in the cost. So I've gotten my mass concentration of what? Pure. And I want to apply the formula which they asked me to calculate the percentage impurity. Now I want to solve that. So percentage impurity will become what? Let's do that. Now, solving the problem, finally, percentage purity, impurity is equals to mass count of impure minus mass count of pure over mass count of impure times 100. So this would be mass count of impure is 6.0 minus mass count of pure is 4.023 over the mass count of impure is 6.0 times 100. And this is equal to what? So we check it out now. 6 minus 4.023 divided by 6 times 100, 32.95. So this is 32.95%, approximately 33%. Because we're supposed to take 3 significant figures, which is 32.9, but this is 5. It comes here to 10. 10 moves down here because it's unstable. It has to move down here to 3, and here becomes 0. So 33.0%. So our percentage impurity in this sense is 33.0%. So we've been able to also solve questions using Redox to solve questions on percentage purity or impurity. So we're going to take a little more to see where we are moving to and the nature of the kind of questions that will be coming. Okay, let's take another one on water of crystallization using Redox, perhaps, so that in any manner you see it, you'll be familiar with it. You wouldn't find that challenging. So it is very important we do. So please, let's take an extra question here, or some extra questions. Okay, I will be taking this out so that I can give us another question. Now, let me read the question thereby after I clean the board and write it up. We say that 0.02 of KMnO4 is titrated against 25 cn³ of iron 2 tetraoxosulfate 6X hydrate. Okay, is that all? Using the balance equation, we should calculate the percentage of iron 2. Okay, that's the mass count, the percentage of iron 2 in the hydrated salt, and the percentage of water of crystallization. So we just move straight up to calculate the percentage of water of crystallization because they didn't give us much. So let me clean this and write out the question so that we'll know what we're dealing with. I think A is still KMnO4 and B is something else. Okay, B is iron 2SO4X hydrate. Okay, that is it. All right, let's take the question up. What is it? Okay, here we are. Now, Concentration of the oxidizing agent, concentration of oxidizing agent is given to be 0.02 mole per dmq. You pay 25 of the reducing agent solution containing this. Put 0.02 mole of KMnO4 in the burette. Pipette 25 of the reducing agent solution containing 27.52 GDM cube of phase. Okay, so here, let me just call it concentration of reducing agent, volume of reducing agent, number of moles of reducing agent, and GDM cube of pure and GDM cube of anhydrous. Let's call it hydrated anhydrous. We're in water crystallization, no more percentage cube. GDM cube of hydrated and anhydrous is what? So let's do the same here. Volume of oxidizing agent, number of moles of oxidizing agent. Okay, that is it. Now 25, here we have 25 cm cube. Okay, containing 27.52 GDN cube of iron 2 sulfate into a conical flask. So 27.52 of hydrated is 27.52 GDN cube. So we're going to find out for that of anhydrous. Okay. So that'll be all. Balance equation. All right. It is not given. Let's see the balance equation. Okay, the balance equation is given here, which is MnO4 minus plus 5 iron 2 plus 8 hydrogen give us Mn2 plus 5 iron 2 3 plus 4 moles of water. So by virtue of this, the number of moles of the oxidizing agent is 1. And the number of moles of the reducing agent is 5. That's strange. Okay, so that is number 1. That has been taken care of. Now they say we should calculate the percentage of water of crystallization. Now, the question is straight up to the end, the percentage of water of crystallization. What is the formula? We know that it is the mass number of the water over that of the whole compound times 100. Now, in order for us to use that, we know that there is X in it. So, we cannot go straight up to start doing that. We have to know what X is. If we know what X is, then we can use that formula. Now, for us to know our X, it has its own formula. It says that the mass ton of hydrated over the mass ton of anhydrous times what? Equals to the mass ton, relative molecular mass of hydrated over the relative molecular mass of anhydrous. So, for us to be able to know the mass ton of hydrated or anhydrous or whatever it is, we must be able to know the molar ton of the sample, which is not given to. So it means that for us to check the mass ton of anhydrous, we must first of all know the molar ton of the salt. So it's an indirect question. They are telling you to do one thing, but there are many other things that have to be done first. So by virtue of that, I know for me to get this, I have to get this first. So though they didn't ask me this, they didn't even ask me this. My understanding of that this guy is involved exposes these other things to me. So now I want to get this, so that I can get this, then I can now get this. So let's move on. First of all, we are going to get the molar concentration of the iron 2 sulfate. That is what we want to do now, the molar con. So permit me, let me take this out. So for us to get the molar con of that, we are going to use our formula as usual. The concentration of oxidizing agent and volume of oxidizing agent over concentration of reducing agent and volume of reducing agent equals the number of moles of oxidizing agent over number of moles of reducing agent. So by that, I'm calculating the concentration of the reducing agent. So my concentration of reducing agent is equals to concentration of oxidizing agent times volume of oxidizing agent times number of moles of reducing agent over volume of reducing agent times number of moles of oxidizing agent. And this is equals to what? So concentration of oxidizing agent is given to be 0.02 mole per dm cube times volume of oxidizing agent. Oh, I didn't take that out. Let me get it. The volume of oxidizing agent is 25.6. 25.6 cm3. So here is 25.6 cm3 times number of moles of reducing agent. Number of moles of reducing agent here is 5. All over volume of reducing agent. The volume of reducing agent is, where is it? Volume of reducing agent is 25 times number of moles of oxidizing agent is 1. Okay, let's confirm if everything is okay here. We have COADA, CRADR equals to NOADs. So for us to get this, we have concentration of oxidizing agent times volume of oxidizing agent times number of moles of reducing agent. That's correct. All over volume of reducing agent times number of moles of oxidizing agent. So we are good. Let's proceed. At 0.02 times 25.6 times 5 divided by 25. That is 0.102, which is 0.102 mole per dm. All right, so we've done that. We're going to move on. So we've gotten our first variable, 0.10. Good. So we're going to move further to get other variables that are required so that we'll be able to see how that goes. 0.102. Now, this is my concentration of what? Base of the reducing agent, which is 0.102 mole per dm3. We are going to now look for the mass concentration of the anhydrous. So I can take this out. Let's look for the other variable before we can go all around. I can equally take this too. All right. Now, I want to get the mass concentration of the anhydrous. The formula says mass con is equals to molar con times relative molecular mass. So the relative molecular mass will be there. So this is the molar con of the anhydrous is given to be 0.102. 0.102 mole per dm3 times the relative molecular mass. Let me just check the one that has been calculated already so that I wouldn't stress myself in going through that. If it is not given, then we'll calculate it. I'm not seeing it. So let's deal with it. So iron here is 56 plus sulfur is 32 plus oxygen is 16 times 4. If I do that, 16 times 4 plus 32 plus 56. That's 152. So I will now have 0.102 mole per dm cube times 152 g mole. And that is 152 times 0.102 will give me 15.5. So this is 15.5. 15.5 what? GDM cube. So if you come back here, here is 15.5 GDM cube. So if you look at this, you understand that that of hydrated must be higher than this. So we've gotten that. We can now proceed further to get the number of moles of water of crystallization now. When we get that, before we can get the percentage of water of crystallization. So we've gotten this. We'll take this out so that we'll be able to calculate the number of moles of water of crystallization, which is the number of moles of air. How many moles are here? When we are done, we are going to name it. All right? So let's take this out now. So, number of moles of water of crystallization is, we have mass con. Let me not write, let me just name it, name and then proceed. Mass con of hydrated is 27.52 over relative molecular mass of hydrated. I just calculated this to be 152. 152 plus x18 equals to mass con of the anhydrous, which is 15.5, over relative molecular mass of the anhydrous, which is 152. If I'm to make S the subject, I cross multiply 15.5 open bracket 152 plus x18 close bracket 27.52 times 152. So 15.5 times 152, 15.5 times 152 is equals to 2356. 2356 plus 15.5 times 18 equals to x 279. This is equals to 27.52, 27.52, okay, times 152, times 152 is equals to 418.03.04. If I make x the subject, my x is equals to this minus this divided by this. So I can just have it directly. This minus this, because of space, minus 2356, 2356, okay, divided by 278, divided by 279, 279, 6.5. So I have 6.5 number of moles, approximately, call it 7. So the number of moles of water of crystallization is 7. 7 means heptahydrate. Hepta, 7. So if that is correct, which it is, we have to now calculate the percentage of water of crystallization. That is where they are taking us to calculate the percentage of water of crystallization. So let's go forward or further to do that. I want to take this out so we can calculate our percentage. So here we go. Now, percentage of water of crystallization is equals to the mass of water, which is X water, over iron 2SO4X water times 100. And this X is 7. or 6.5, 7 times 18 over 152 plus 7 times 18 times 100. So if I do that, let me take it over to this other side. Now if I do that this other way, this is what we're going to get. 7 times 18 will give us, 7 times 18 will give us 126 over, means this is 126 plus 152 plus 152, this is 278, 278 times 100, and this is 126 times 100 divided by 278, that is 45. 45.3%. So the percentage of water of crystallization is 45.3%. So now questions like what is the name of the salt may arise, and that will be required of you to be able to tell us. So this was officially FeSO4X water, but it's now FeSO4 7 moles of water. So this is iron 2 tetraoxosulfate 6 heptahydrate. You may be required many a time to do that, and whenever you are required, just proceed further to do it. Okay, maybe we should just take one more or a couple more so that we can call it off. Now, my business today, importantly or interestingly, has been on our calculations that involve redox. And you must take it very serious, because if that is my focus, that should be your focus too. So you should take it very seriously and concentrate on it, especially in terms of balancing of redox equation, in terms of your oxidation number, how to calculate your oxidation number, because you can't do nothing about balancing of redox if you don't know how to calculate your oxidation number, so you must know all of that. Then that aside, and its application in terms of calculating amount of substances, calculating the relative molecular mass, calculating the mass concentration, the molar concentration, and so on. You should be able to know how to use redox to achieve that. If you do not know how to use redox to achieve that, that becomes a problem. So you should know that. And I've solved questions around that will be able to trace our routes to know where we're going and where we're coming back from. So I'm going to solve maybe one more question, maybe outside of redox, so that we can see how all of these things work. And we can call it off from there. The question says some crystals of washing soda were exposed to the atmosphere for efflorescence to take place. Now 6.02 grams of this partly effloresced washing soda, which is sodium triisocarbonate Y hydrate, were then dissolved in 500 cm3 of water. 25 of this triisocarbonate solution required 32.10 of 0.097 mole per dn³ hydrochloric acid. Hydrochloric acid for complete neutralization. Calculate Y, hence write the formula of the effloresced washing soda. So that's where we are going to. It's not just, I don't know, we are going straight up to just calculate the percentage of water of crystallization. Remember, they gave us 6.02 grams of this partly effloresced washing soda in 500 cm3, which is the mass concentration of the water of crystallization. That's hydrated. So we have to calculate that of the anhydrous. Then when we do that, we'll be able to determine our value Y. For us to get Y, you know what it is. When we get Y is the number of moles of that. Then we can proceed further to get our percentage if they ask us, but they did not. So if we get Y, we can stop there. Okay? We can just stop there and the whole thing goes on. Okay, let's see to that. Or better still, I think if we can take the last question as assignment, that is also important. I shouldn't just solve everything. You solve it as assignment and send the answer to this platform. Go to the comment section and send the answer to to that place. I'll see it. I am intending to shut down because of the noise downstairs. It seems to be impeding what we're doing right now. It's much, so we can take that as an assignment. So because of that, I would like to read the question one more time so that you know or get it clearly. I say, some crystals of washing soda were exposed to the atmosphere for a fluorescence to take place. 6.02 grams of this partly effloresced washing soda, sodium trisulcarbonate 4Y hydrate, which is this is the compound. We say 6.02 grams of this partly effloresced washing soda, which is this, were then dissolved in 500 cm cube of water. 25 cm cube of this trisulcarbonate 4 solution required 32.10 cm cube of 0.097 mole per dn cube hydrochloric acid, which is HCl for complete neutralization. Calculate Y. You should find the value of Y, which is over there. Hence, write the formula of the effloresced washing soda. So let me break it down. When you have looked for the number of moles of water of crystallization, which is your Y, whether is it 10 or is it 20, is it 30, then you come back, replace it into this formula. If it is 5, it is becoming, you now call it sodium trisulcarbonate 4 pentahydrate. That becomes the name. If it is 10, it's decahydrate, and so on and so forth. If it is 7, it's heptahydrate. If it is 8, it's octahydrate. If it is 2, it's dihydrate, monohydrate, if it is 1. So don't forget, that is what they want from you. So we're going to cut it off now. We've done justice to the basic things which are required of us. I've told us my interest, the areas which I am concerned, which is this redox calculations. You must get yourself acquainted with it. And especially you should also know the formulas for percentage purity, water of crystallization. Others are relatively simple, so we don't deal with them that much. But all the time, we always have questions and that comes out from this water of crystallization and percentage purity, and they will always come out. So also, especially when it comes to redox, for those of you who do not understand the basic principles of balancing of redox equation, which is essential to our understanding of what we're dealing with here, should go back and check the video on redox calculations where you're going to see that and work on it. It is that important. So I urge all of you to do the needful. Reach out to me when necessary where you do not understand, so that I'll be able to sort it out for you, even in class or online. You can send your stuff to me, your questions there. I will address them. It has really been a pleasure, a privilege being with you today. I urge you all to have a beautiful time and take care of yourself. See you again when I see you. Bye.